This example says, suppose a spring has natural length 3 feet and it takes 10 foot-pounds to stretch it from 5 feet to 8 feet. How much work is required to stretch the spring from 4 feet to 7 feet? Now, before we even begin with this, we don't know the spring constant K. Okay, so in order to find this work, we actually need to use what's given to us in the beginning in order to find K. So we need the spring constant K. And the way we're going to do this is we're going to use that the work is equal to 10 foot-pounds when we stretch it from 5 feet to 8 feet. Now, the only thing we have to be careful about is when we're doing these spring problems is that it's telling us that it's stretched from 5 feet to 8 feet, but this is relative to the end of the spring, okay, or relative to the beginning of the spring, rather. So what do I mean? So I'm going to draw this spring over here, like this. Okay, it was originally 3 feet, right? And so I'm thinking of this as where I'm starting when I write down these numbers 5 and 8. So we're going to go out to 5 feet and stretch it to 8 feet. Okay, this is what we want to do. But when we're computing work, we're only concerned about starting from the end of the spring when it's in equilibrium. In other words, when I compute the work integral here in a second, I only need to know the difference between 5 and 3 and 8 and 3. So here, this length is going to be 5 minus 3, which is equal to 2. And this length here is going to be 8 minus 3 is equal to 5. So when I write down this work integral, work is equal to 10, this is going to be the integral of kx dx, and our goal is to get this k. And I'm not going to use 5 and 8. I'm going to use 2 and 5 as the limits of this integral. So now all we have to do is compute out this integral, and we can solve for k. So this is going to be k times x squared over 2, adding 1 to the power and dividing by it, and evaluating from 2 to 5. And so this is going to be equal to k times plugging in 5, that's 5 squared, so 25 over 2. And then minus plugging in 2, so 2 squared is 4 over 2. And the reason I'm not simplifying this is that I want to keep this common denominator. So if I go ahead and simplify everything out, I get the equation 10 is equal to k times 25 minus 4, which is 21, over 2. And so I can multiply by 2 over 21 in order to cancel this out to get that k is equal to 2 over 21 times 10, which is just 20 over 21. Now, this gives me the spring constant k, but remember that our goal is to actually do part A. We want to find the work that's required to stretch the spring from 4 feet to 7 feet. So we're going to do something very, very similar to what we did here. We're going to compute this integral, but now we know k, and we just have to worry about these limits changing. Okay, so part A, the work is going to be the integral of kx dx, and we'll plug k here in a second as well. And again, we want this in reference to the end of the spring. So this isn't going to be 4 to 7. This is going to be 4 minus 3 and 7 minus 3. That will be computing this integral with respect to. And now let's go ahead and plug everything in and compute. So this is going to be from 4 minus 3, which is 1, 7 minus 3, which is 4, 20 over 21x dx. And all we have to do is compute this out in the exact same way. So I'm going to do 20 over 21, and then x squared over 2. And let's go ahead and pull that 20 over 21 out and evaluate this from 1 to 4. So if I plug if I plug this in, what do I end up with? I'm going to end up with 20 over 21. And then 4 squared over 2, this is going to be 16 over 2. And then minus 1 squared over 2, so minus 1/2. Again, I didn't simplify this because I want common denominators. This is 15 over 2. And then finally, what I can do is I can go ahead and cancel out the 2 and the 20 and make this 10. And so this is 10 times 50 over 21. And so this means that the work is going to be 150 over 21. And just to be careful, let's go ahead and write down the units. This is foot-pounds. And that's it. Okay, now let's go ahead and look at part B. This one says, how far beyond its natural length would a force of 3 pounds keep the spring stretched? Now, this one is actually much shorter than part A. We know that the force formula is equal to K times X, and it tells us that the force is equal to 3 pounds. And then we know the K from the last slide, this is going to be 20 over 21. And so what we want to do is we want to find this X. Okay, so all we have to do is solve 3 is equal to 20 over 21 times X. And so that means we're going to multiply both sides of this by 21 over 20. And so X is going to equal 63 over 20 feet. And that's all it wants.